Hello and welcome to G Fun Facts Online, the show where we dive deep into the most amazing corners of science and the natural world. Today, we're talking about armor, not the clunky medieval suits of knights, or even the advanced Kevlar vests of today. We're looking at nature's designs. For millions of years, while humans were just figuring out pointy sticks, creatures great and small were already perfecting the art of self-defense, evolving intricate, highly effective armor to survive. Now, in a fascinating field called biomimicry, scientists and engineers are looking at these natural masters of protection for inspiration. They're studying the remarkable properties of the world's toughest creatures and translating those designs into revolutionary protective gear for us. So get ready to meet the superheroes of the animal kingdom, whose biological blueprints are shaping the future of human protection. First up, let's journey to the deserts of North America to meet a creature that seems to have a superpower, near indestructibility. Imagine a small, unassuming insect. Now, imagine it getting run over by a car and just walking away afterward. This isn't a comic book scene. It's a regular Tuesday for the Diabolical Ironclad Beetle. This little tank of an insect can withstand forces up to 39,000 times its own body weight. To put that into perspective, that's like an average 200-pound person being able to support the weight of about 40 M1 Abrams battle tanks stacked on top of them. It's a level of durability that seems to defy the laws of physics. So, what's its secret? How does this tiny, flightless beetle achieve such incredible crush resistance? The answer lies in the brilliant architecture of its exoskeleton. Many beetles have wing covers, called elytra, that can open up to allow for flight. But the Diabolical Ironclad Beetle gave up flying long ago. Instead, its elytra have fused together, forming a solid, continuous shield over its back. But this shield isn't just one solid piece of chitin. If it were, it would be strong, but also brittle. A sharp impact would likely shatter it. Instead, the beetle's armor is far more sophisticated. Running down the center of its back is a suture, a line where the two halves of the elytra meet. But this isn't a simple seam. It's a series of interlocking, jigsaw-like pieces. Think of two puzzle pieces fitting perfectly together. These connections are made of layers of tissue, held together by proteins. When the beetle is subjected to immense pressure, say from the tire of a Toyota Camry, something incredible happens. The layers don't just snap. Instead, they subtly give way, one by one. The scientific term is delamination. This layered, interlocking design allows for what engineers call graceful failure. The structure absorbs the impact energy by controllably pulling apart in these tiny layers, preventing a single, catastrophic crack from ripping through the entire exoskeleton. This allows the beetle to survive forces that would turn any other insect into a tiny smear on the pavement. Scientists are, of course, fascinated by this. By 3D printing materials that mimic the ironclad beetle's layered and interlocking sutures, they're hoping to create a new generation of materials. We could see this design principle used in everything from more effective body armor that can absorb impacts without shattering, to stronger and safer components for buildings, bridges, and vehicles. All thanks to a little beetle that decided trading flight for a tank-like body was a good evolutionary deal. From the dry deserts, let's plunge into the murky, dangerous waters of the Amazon River basin. This is a place teeming with life and with peril. And one of the most famous perils is the piranha, a fish renowned for its razor-sharp teeth and voracious appetite. Yet, living right alongside these swimming scissors is the arapaima, one of the world's largest freshwater fish. How does this giant fish thrive in a piranha-infested environment? The answer is in its scales. The arapaima's armor is a masterclass in composite design. Each scale isn't just a single hard plate, it's a sophisticated two-layer system. The outer layer is exactly what you'd expect. It's hard, bony, and highly mineralized. Its job is to be the first line of defense, to resist the initial penetration of a piranha's bite. It's designed to be tough enough to stop that razor-sharp tooth in its tracks, but hardness often comes with a trade-off: brittleness. A hard material can crack under pressure. This is where the arapaima's genius second layer comes in. Beneath that hard exterior is a much softer, more flexible inner layer made of a protein called collagen. But this isn't just a simple cushion. The collagen fibers are arranged in a special spiraling pattern that scientists call a boulogond-like structure. Imagine layers of plywood, but instead of each layer being at a 90-degree angle, each layer is slightly rotated, creating a spiral or helix as you go down. This structure is the key to the scale's toughness. When a piranha bites down with all its force, the hard outer layer does its job and spreads the impact. If the bite is strong enough to cause a tiny crack in that outer layer, the boulogond structure of the inner layer takes over. The spiraling collagen fibers prevent that crack from growing and spreading. They effectively contain the damage, dissipating the energy of the bite and stopping it from reaching the fish's soft body. This combination of a hard, puncture-resistant outer layer and a tough, energy-absorbing inner layer makes the arapaima scales both incredibly durable and remarkably flexible. The fish can swim and move with ease, yet it's protected by an armor that engineers would love to replicate. And they are. The design principle of the arapaima scale is a direct blueprint for developing advanced body armor for soldiers and law enforcement, armor that can be lightweight and flexible enough for active duty, yet tough enough to stop a projectile. Now, let's go from the Amazon to one of the most extreme environments on Earth: deep-sea hydrothermal vents, thousands of feet below the ocean surface. Superheated, mineral-rich water blasts from the seafloor, creating a habitat that seems completely alien. And in this hellish landscape lives a snail with a suit of armor, straight out of a fantasy novel. Meet the scaly-foot gastropod, a creature affectionately known as the iron-gilled snail. This snail does something no other known animal on the planet can do. It builds its shell using iron, specifically iron sulfides, which it incorporates directly into its shell structure, creating a natural suit of iron armor. The snail's shell is a three-layered marvel of defensive engineering. The innermost layer is made of aragonite, a common calcium carbonate material found in many mollusk shells. But then it gets weird. The middle layer is a thick, soft, organic layer called the periostracum. This layer's main job is to act as a shock absorber. It's the padding inside the armor. But the real star of the show is the outer layer. This layer is embedded with granules of iron sulfide, essentially giving the snail an iron-plated shell. This unique defense isn't just about being hard. It's designed to manage an attack in a very specific way. A common predator in the snail's neighborhood is a crab, which will try to crush the shell with its powerful claws. When the crab clamps down, the iron-infused outer layer is actually designed to crack. But it cracks in a very controlled way, creating a web of tiny micro-cracks that absorb a huge amount of the attack's energy. This prevents a large, fatal fracture from forming. The energy that gets through the cracked outer layer is then met by the thick, squishy organic middle layer, which dissipates the rest of the blow, protecting the fragile inner shell and the snail itself. It's an incredibly sophisticated, multi-layered defense system, and it has absolutely caught the eye of military researchers. They see the iron snail's shell as a potential blueprint for designing next-generation armor for soldiers and vehicles, armor that doesn't just block an impact, but actively manages and dissipates its energy, providing far greater protection against bullets and explosions. From a creature built to withstand crushing forces, let's turn to one designed to deliver them. The mantis shrimp is one of the pound-for-pound strongest animals in the ocean. It's a small crustacean with a big reputation, mostly thanks to its club-like appendages. It can whip these clubs forward with the acceleration of a .22 caliber bullet, generating a force so powerful it can shatter crab shells, dismember prey, and even crack the glass walls of an aquarium. The impact is so fast, it actually boils the water in front of it, creating a shockwave that can stun or kill prey even if the club itself misses. For years, the question that fascinated scientists was simple. How can the mantis shrimp deliver such a devastating blow over and over again without completely shattering its own weapon? The answer, once again, is in a complex, multi-layered structure. The very surface of the club, the part that makes contact, is made of a dense, hard, ceramic-like material. It's built for withstanding intense impact. But just like with our other armored friends, a hard material by itself would be too brittle. The real magic lies just beneath the surface. Below the impact region are layers of chitin fibers, the same stuff most insect exoskeletons are made of, but they are arranged in a helicoidal or spiral structure. This is very similar to the bulligan structure we saw in the arapaima scales. This spiral staircase of fibers is the secret to the club's incredible resilience. When the mantis shrimp smashes its club into a target, the impact inevitably creates tiny microcracks on the surface. In a normal material, these cracks would travel in a straight line, growing larger and larger until the entire structure fails catastrophically. But in the mantis shrimp's club, a crack is forced to follow the twisting path of the spiral fibers. This twisting journey dissipates a huge amount of energy, slowing the crack down and preventing it from spreading. It ensures that any damage is localized and doesn't lead to a complete failure of the club. This remarkable ability to absorb and dissipate shock has inspired researchers to develop new composite materials for all sorts of applications. Imagine a football helmet lined with a material that mimics the mantis shrimp's club, dramatically reducing the risk of concussion. Or body armor that can take multiple hits without losing its structural integrity. The mantis shrimp's incredible punch is teaching us how to build things that are not just strong, but incredibly tough and resistant to impact. Finally, let's address one of the oldest problems in armor design, the trade-off between protection and flexibility. Hard, rigid armor offers great protection but can severely restrict movement. Softer, more flexible armor allows for better mobility, but often at the cost of safety. It's a dilemma that has plagued armor designers for centuries. But, of course, nature has a solution. Meet the chiton, a type of marine mollusk that looks a bit like a flattened, segmented woodlouse. Instead of a single, solid shell like a snail, the chiton's back is covered by 8 separate, overlapping mineralized plates, all embedded in a tough, flexible muscular girdle that is itself covered in tiny, fish-like scales. This segmented design is the key. It allows the chiton to be both highly protected and incredibly flexible. It can bend and contort its body to cling tightly to the uneven surfaces of rocks in the turbulent intertidal zone. When the chiton is just moving around, its plates and scales can slide over one another, allowing for a wide range of motion. It's flexible, but the moment a predator, like a starfish or a seabird, tries to attack, the system changes. The plates and scales lock together, forming a continuous, rigid, and highly protective barrier. This ability to instantly transition from a flexible state to a rigid one is a holy grail for armor design. And scientists are already hot on the trail. Using 3D printing, researchers have created prototypes of flexible armor inspired by the chiton. They've printed hard, rigid scales onto a flexible substrate. The resulting material can be bent and twisted, but when an impact occurs, the scales lock together to resist it. This research could lead to incredible new types of body armor. Imagine a suit that is soft and flexible around your joints, like your elbows and knees, allowing for complete freedom of movement, but becomes rigid and protective over your torso and vital organs. It would be a suit of armor that offers the best of both worlds, robust protection and enhanced mobility, creating a more effective and less cumbersome defense for anyone who needs it. So what does this all mean for us? All these lessons learned from beetles, fish, snails, and shrimp are directly informing the design of the next generation of human augmentation. We're talking about exoskeletons. Early exoskeleton designs, like the famous BLEEX from Berkeley or the HAL5 from Japan, were focused primarily on power and carrying heavy loads. They were amazing feats of engineering, but they were often bulky, rigid, and didn't offer much in the way of integrated protection. Now, however, newer designs are incorporating these biomimetic principles. Scientists are creating exoskeletons for rehabilitation that use cable-driven systems inspired by the adaptive armor of a shrimp's shell, making them more comfortable and adaptable to a patient's body. The work on chiton-inspired armor could be integrated into full-body military exoskeletons, providing comprehensive protection without turning a soldier into a stiff, awkward robot. As our technology allows us to see deeper into the intricate structures that nature has built, our ability to copy those designs grows. By learning from the blueprints perfected over millions of years of evolution, we are on the verge of developing protective systems that are not just stronger and lighter, but smarter, more flexible, and more adaptable than anything we've ever created before. The future of armor isn't just about inventing new materials in a lab. It's about looking to the natural world and realizing that the best ideas have been there all along, waiting for us to be clever enough to copy them. Thanks for tuning in to G Fun Facts Online. Join us next time as we uncover more of the incredible science that shapes our world.